Hello, I'm Mochandra, and I'm the NPTEL TA for this course, Material and Energy Balances. We are now in the week three of this session, of this problem solving session. So, brief introduction about me. I am a PhD scholar in the Department of Chemical Engineering at IIT Kanpur. My research area is tissue engineering and 3D bioprinting. If you'd like to know more about my research, feel free to visit my website. And if you have any course related queries, I request you to post it on the course forum, or you can reach out to me as well. My email ID is given on the screen. Every Saturday from 3 to 5 p.m., we are meeting for this session, and it will go on till 12th April. That is the last week of this course, 12th week of this course. And the meeting platform will remain same, that is MS Teams. The link has been provided to you every week. NPTEL team sends you the reminder for it. So the link is attached in that mail. The recordings are made available to you in my YouTube channel. You can go ahead and subscribe so that you will get notified about the recording after it is posted. And notes are also made available to you through Google Sheet. If you just quickly go to your NPTEL login and check the left hand side where you find the week wise content. So, there, one section they have made called problem solving session. So if you just click on it, you will find the notes as well as the recording links. Every session, the number of participants has been recorded as well as their name. Okay. So I request you to, join and maintain a good attendance. Okay. In this meeting platform, you are not having a chat option with you. So if you have any queries, you have to unmute yourself and speak basically. But I would request you to don't unmute yourself unless you really have to speak. If there is some background noise, it can really cause disturbance, right? So just good note on that. So this week we will discuss some problems based material balance with chemical reactions. Okay. So this is the first problem that I'm showing on your screen. I'll give you a few minutes. Please have a read. So the problem states that there is 100 moles of SO2 and 100 moles of O2 that are being fed to a reactor, and they react according to this chemical reaction. Okay. First, we have to find the limiting reactant in this reaction. What is the excess reactant? Then also we have to find the percentage excess, percentage conversion of SO2, and percentage unreacted of O2. So how should we proceed with the first part? Tell me. If you have done similar problem, uh, you can give it a guess on how should we find the limiting reactant, or what is the limiting reactant you think in this case?
the with the basis of molecular weight.
I'm sorry, which one is the limiting reactant? Is it SO2 or O2?
We need to calculate on the basis of um, molecular weight.
So we can actually do the first part without knowing the molecular weight just by looking at the stoichiometry.
That is
Okay.
the
Uh,
O2 is the limiting agent.
O2 is the limiting agent. Okay, let's see. Let's try. Okay. So what we are given is that this is the reaction. Let me quickly write it down. 2 SO2 plus O2 gives 2 SO3. is the reaction given to us. And we also know SO2 number of moles that is entering is 100 moles for SO2, and for O2 also it is 100 moles. These are the entering species, input species. Okay. So as per stoichiometry, if 100 moles of SO2 is there, okay, then how much of O2 will be required? So stoichiometric ratio of SO2 to O2 is what? 2 is to 1, correct? From the reaction. So again, the question is, if 100 moles of SO2 is present, then how much O2 is required? Tell me.
I didn't understand. Can you explain again?
So we have to find what is the limiting reactant in this case, whether it is SO2 or O2. So in order to do that, we have to see the reaction first, and we have to see how much quantity of each of the reactant is present in the reaction. So we have to verify whether the given amount of reactants that is available to us matches with the stoichiometry. Okay. So my question is, if there is 100 moles of SO2 present, so so as per stoichiometry, how much O2 will be required? So if 2 moles of SO2 is there, then 1 mole of O2 is required. So if 100 moles of SO2 is there, then we require
50 mole of
50
O2.
moles, correct? Yes, as per stoichiometry. Okay. If we do conversely, if 100 moles of O2 is there, then how much SO2 will be required as per stoichiometry?
50.
No, no, not 50, 200, right?
Yeah, 200.
200, correct? So, but what is given to us? What is actually fed? Actual values that are fed is 100 moles of SO2 is there and 100 moles of O2 is there. But stoichiometry dictates that we need 50 moles of O2 and 200 moles of SO2. So, which is the limiting reactant in this case?
Here is the yes, O2.
SO2, right? Because we need more, right? Stoichiometry
Correct.
dictates that we need 200 moles, but we are only given 100 moles. So the limiting reactant is SO2 in this case. That is part A answer. Now part B asks, and what is the excess then? O2 is the excess.
Correct. Yes.
This is the part B answer. Now, what is the percentage excess then? So finding the percentage excess. So we are given 100 moles of O2, but we only required 50, okay, divided by the stoichiometrically valid number of moles, 50. So it will be how much?
1.
Sorry, 200. It will be 1 means 100% excess is there. Okay. This is part C. Done. Next, what is the percentage unreacted O2? Okay, percentage unreacted O2. Okay, so we have to find that. In order to do that, we have to see how much of the limiting reactant, because hmm, whatever O2 that is reacted is because it has uh, completed when it underwent reaction with SO2. Okay, so we have to determine how much of the limiting reactant is reacted, that is SO2, how much number of moles of SO2 is reacted divided by total number of moles that is there. Okay, so that is how we will do. Let me write it down. Let's find out the fractional conversion of SO2. Why we are doing this? Again, why we are doing this? Oh, sorry. Um, part C we did, no? Part D. We have to do part D. I'm sorry. Let's do part D first. We have to find the percentage conversion of SO2. But first, let's find the fraction. So then if it multiply with 100, we will get the percentage. So fractional conversion of SO2. So basically moles of SO2 that is reacted by total moles or species fed to the reactor. So since SO2 is the limiting reactant, so all of it will be consumed. So it will be 100 moles, and total moles means 200. 100 plus 100. This is the fraction. The percentage conversion is 50%. So this is part D. Understood? How did we calculate the fractional conversion of SO2? This is part D. Is it clear?
Yes. Yeah.
Then we have to do part E, that is percentage unreacted O2. So O2 is excess, right? So let's call this fraction as F. Okay. This will be 1 minus F into 100. Why? Why this will be like this? See, whatever O2 that is remaining unreacted is because the limiting reactant SO2 is consumed, right? And we know from part D how much of SO2 is converted, the fraction of how much out of total, how much of the SO2 is converted, and we got it in a fraction form. Okay, so whatever is remaining in the reactor is O2. There is no other species other than O2 that can be present. That is why percentage unreacted O2 will be 1 minus F into 100. So F we already calculated. F is half into 100. So it will be 50%. So 50% of the O2 will remain unreacted, and rest 50% of SO2 is the conversion percentage. Is it clear?
Yeah. Yes.
Now let's go to another question. Very similar to this question is very similar to the first one. I'll give you a few minutes, have a read on your own, and then I'll start. Done? Done with the reading? Okay. So the question states that antimony is obtained by heating pulverized stibnite. So this pulverized stibnite is actually Sb2S3 with scrap iron and drawing off the molten antimony from the bottom of the reaction vessel. So this is the chemical reaction. Let me write it down. Sb2S3 plus 3Fe gives 2Sb. Sb is antimony. Okay, it's a metal called antimony. 2Sb plus 3FeS. This is the reaction. Now suppose you are given zero point 0.6 kg of Sb2S3, 0.25 kg of iron. So let's write the mass that is given to us. Sb2S3 is 0.6 kg. Fe is iron is 0.25 kg. What it should be kg. Then the product antimony is 0.2 kg. Only this much is given to us. FeS mass is unknown. Okay, so these are the values and reaction that is known to us. First, we have to find in this reaction what is the limiting reactant. Now tell me, from the mass itself, can you determine the limiting reactant?
Yuppie.
Maybe. Did you say maybe?
No, yuppie.
Fe. So, oh, nice. Fe, you did correct. How did you do it? How did you guess Fe is the limiting reactant? You're correct, by the way. Fe is the answer. Did you just guess based on the mass values because Fe is less in quantity or something like that? How did you guess? Okay, let me do it. If the way I'm doing it is the same way that you did, let me know. Okay. So we are given just the mass values. First, we have to convert it into moles. So in order to do that, we have to first know the molecular weights. So the molecular weight of Sp2S3 is 339.7 gram per mole. Fe is 55.8. Sp is 121.8. And for Fe is 87.9. This is the molecular weights of all the
Hello.
species. Hi, hello. Yes, yes, you have
Actually,
joined back.
actually,
Yeah,
some network issues there. That's why I think
it's fine.
I didn't get your voice.
Okay, it's fine.
Can you
I'll
explain
repeat.
again?
Yeah, yeah, I'll repeat. So, um, we are given the mass from the question. So from the question, we have to first determine how much of the moles that are actually present. Because then what we'll do, we will compare the number of moles given to us with the stoichiometrically valid required number of moles and see whether we have the enough number of moles that matches with the stoichiometry or not. And then we will calculate, or then we will determine which is the limiting reactant. That's the procedure, general procedure to do this. So I just wrote down
I,
the molecular.
your voice is breaking. Just give me 1
Hello.
minute.
Okay, okay, yeah. Please join back if there is some network issue or something like that. Yes, can you hear me now?
Now it is clear. Okay.
It is clear. Okay. So as I was saying that first we have to check what is the number of moles of the species that we are given to us and whether that it matches with the stoichiometrically relevant number of moles or not. Okay, so from known, we know the molecular weights, or we can determine the molecular weights by just giving Google search or something like that, and these are the molecular weights of each of the species. So from the molecular weights you have to first calculate the moles. So for Sp2, S3, the number of moles will be zero point 0.6 kgs. So 1000 divided by 339.7. So if you do this, meanwhile you calculate and let me know what is the number of moles that you're getting. So similarly for iron, the number of moles will be 0.25 into 1000 divided by 55.8. For Sp, the number of moles will be zero point 0.2 into 1000 divided by 121.8. So, what's the values that you're getting for each? Let me know.
I didn't calculate actually. I'm using mobile now.
Oh, it's fine. Okay. So for Sb2, S3, it is 1.77 moles. For iron, it is 55.8. So it is for 4.48 moles, and it is 4.48 moles. And for antimony, it is 1.64 moles. So these are the given number of moles of the reactant as well as the product antimony. So now we have to check which is the limiting reactant here. So we will use the same logic that we did previously. So if we see the stoichiometric ratio of Sb2S3 to Fe, what we see it is 1:3 or 1/3, means 1 mole of Sb2S3 requires 3 moles of Fe. Okay, so if now we are given 1.77 moles of Sb2S3. So this means we require, stoichiometrically, we require how much? 3 into 1.77 moles. That is, we need 1.77 into 3. We need 5.31 moles. Okay, but what is given to us? 4.48 moles. Let's do the other way. We are given 4.48 moles of Fe. Just to check. So from the first this statement, it is quite clear that Fe is the limiting reactant, but we should otherwise check as well whether Sb2, what's the required number of moles for Sb2 and whether we are given that much or not. So if 4.48 moles of Fe is given to us, that is the true value. Then stoichiometrically, how much Sb2 S3 is required? It is 4.48 divided by 3, correct? So it is 4.48 divided by 3, 1.49 moles. This means what? These two values and these two values. What does these show? It shows that if we shows Fe is limiting reactant because we need 5.31 moles, but we are only given 4.48 moles. Okay, so Fe is limiting reactant, whereas Sp2S3 is the excess. Because we have 1.77 moles, but we only needed 1.49 moles. So this is the Fe is limiting, and Sp2 is the excess. Did you, when you said Fe is limiting, did you also think in this way? Like, how did you just simply guess with your gut, like whatever seemed appropriate, you just guessed it? Was like, did you understand the procedure first, and then if you have any doubts, let me know.
No, I was just guess.
You did this? Oh, nice, great. So this is for answer for part A. Okay, part A is done. What's part B? Part B states find the percentage of excess reactant. Can you now tell me what is the percentage of excess reactant? Or how should I calculate? The excess reactant is Sb2S3. Okay.
Yes.
Yes. So how do we calculate the percentage excess reactant? We are given 1.77 moles, but we only need 1.49. This is the excess amount divided by 1.49 moles into 100. Okay, so if you calculate this, you will get the excess reactant. Can you calculate and let me know what's the value? Are you doing it?
15.48. So
18.48. Did you say 18.48?
15, 15, 1.
I'm sorry. And your voice broke. Can you repeat?
1.48.
Actually, your answer is not matching with the correct one. Let me try it myself.
Hello. 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 Your voice is not getting. I'm not getting your voice. No voice. Hello. Your voice. Hello. Hello. I. You are not audible. Hello. Hello.
Hello, can you hear me now?
Yeah. 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 It is audible. No
Okay.
audible.
Okay.
Okay. That is
So,
18.8. Correct.
yes, yes. Okay. So let's now proceed with part C. We have to find the degree of completion. Basically, it's in the fraction form. So how shall we do it? So the final product that we are expecting is SB. So we can degree of completion, and we know that the reaction completed and the product is SB. So we will use this chemical reaction with respect to SB. So according to the reaction, we need 3 moles of Fe to give 2 moles of Sb. This is what the reaction states. Okay. And we also know how much of the Sb is produced. That is 1.64 moles of Sb is produced. This is the produced value. Now we have to find the fraction or degree of completion. How shall we find degree of completion? We will basically determine how much Fe is utilized, which is given to us. So we were given Fe 4.48. Okay. To produce 1.64 moles of Sp. This is the question that we have to answer. How much Fe is utilized? Fe, since Fe is the excess reactant, so the reacted product, how much of the Fe will be reacted, that will be corresponding to that means that much of the Fe has been utilized or consumed to produce Sp. Okay, we are not choosing the ore as Sb2 S3 ore for that. Okay, I think we can do that other way as well. So, but let's do in this way. So we know 3 moles of Fe is needed for 2 moles of Sp, and we have produced 1.464 moles of Sp. So how much Fe is utilized? This is the question. 1.5 into 1.64. So 2.46 mole of Fe is utilized. So degree of completion then is a fraction, basically moles of Fe utilized divided by total moles of Fe, okay, that you used initially. So it was 2.46 divided by total moles of Fe is 4.48. So it is 2.46 divided by 4.48. So 0.55 is the fraction value, or it is 55%. The up to 55% the reaction has completed. Alternatively, you can do this part by considering Sb to S3 as well. So we know 1 mole of Sb2S3 from the reaction. We know let's do the alternate way as well. We know 1 moles of Sb2S3 is needed for getting 2 moles of Sb. We have so and we have 1.64 moles of Sb with us. So how much Sb2S3 is required? So it will be 1 mole of Sb2S3 by 2 moles of Sb into 1.64. Yeah. So this will be 0.82 moles of Sb2 S3 is needed for getting 1.64 moles. So degree of completion now will be calculated in terms of Sb2 S3. So moles of Sb2 S3 utilized that we just calculated by total moles of Sb2 S3. So it is 0.82. What is total moles? Total moles is 1.77 moles. Now, if you do this, we'll get close to 0.46. It is not coming as same. Maybe I've done some calculation error. It's fine. It's fine. The anyway, the previous one is correct. This method is correct. Yeah, let's not do this one then. Or you can later on check yourself. Maybe I have done some calculation error due to hurrying, but this is the correct way of doing this part. All right. Any doubts? Any comments?
No, it's okay.
It's okay. All right. Then we have to calculate the percentage conversion. So percentage conversion will be now calculated based on this was part D. Oh, sorry. This is part D, percentage conversion. So again, the product is SB, but for this part, we will consider the limiting reactant SB3 and the product is SB. We will choose these two components for calculating this. So as I tried to do previously, I showed that 1 mole of Sb2S3 reacts to give 2 moles of Sb from the reaction. Okay. And we already have Sb 1.64 moles. So how much Sb2 is needed then? As per stoichiometry, it will be 1 by 2, 1 mole Sb2 by 2 moles Sb into 1.64. So this will give you 0.28. Okay. And so percentage conversion will be moles of Sb2 S3 required by total moles of Sb2 S3. So it is 0.8 to 1.77. So I did it previously. It was coming close to, there will be 100 here, 46.3%. Okay, this is the percentage conversion. So degree of completion and percentage conversion. These are two different things, which I realize now. Also, you should note. Means when we are talking about degree of completion, then we are considering the excess reactant for the calculation. Because after all, after the reaction is completed, it is the excess reactant that will be remaining. So that, based on the amount of excess reactant, we are calculating the degree of completion. Whereas in percentage conversion, we know the limiting reactant will be consumed completely. So the product that we are getting SB, that's the same in both the cases. But for getting the percentage conversion, we are considering the limiting reactant. Okay. Please take a note of this. If you are asked a similar thing later on, you will know which reactant to use for calculating which type of question that is asked. All right. So the last part, E, we have to calculate the yield. So what is yield? What do you understand by yield? What do you mean by yield? Any idea?
The percentage of product, final product.
So yield is expressed as form of a ratio. So it is the ratio of how much product that we got. So in this case, product is SB. So mass of SB by how much reactant that we have consumed. So for calculating yield, we are considering the limiting reactant. So we are considering the mass of the limiting reactant. So in the question, SB was zero point 0.2 kgs and SB to S3 is 0.6 kg. So it will be zero point 0.2 by 0.6. So yield is one third, right? This is how you will calculate the yield. Any questions?
Mm. Actually, this why this conversion is not happen 100%. I didn't understand. This percentage conversion is 46.3%. If we are seeing the reaction, we have excess reagent. Then why ESP is not yes ESP to ES3 is not converted in ESP?
See, you are thinking in the sense that Sb to S3 is a limiting reactant, so it will be consumed completely, right?
Correct,
That is
correct.
that is what you are thinking. But look at this. Look at this part that we did. Here we are given the number of moles of Sb that actually has been produced. All right, that is the actual value from the reaction that they got is the Sb. So based on those number of moles, how much of the Sb will be consumed now? That's the question. Stoichiometrically, we know 1 mole of Sb to S3 is reacted with 2 moles of Sb. But the actual reactor where the reaction is happening, there we got only 1.64 moles. Then how much of the moles of Sb2S3 is actually utilized? That's the question. So when we uh, did this calculation, we got 0.82 moles. So now the percentage conversion will be based on the limiting reactant. So it will be number of moles of Sb2S3 that is utilized, it is 0.28, by total number of moles that we were given to us.
Okay.
Mhm. Maybe reflect on this later on. It will get understood. Like I know it's a bit tricky. It's I understand that part, but just practice similar problems and it will make sense. All right, it will make sense. So let's move on with the third question. Um, just quickly have a read while I drink some water. So in this question, there is what? There is a absorber column. Okay, let's try to draw so that we will understand better. This is a column and the feed. What is the feed? Feed is N2 and CO2. 80%, 80 mole percent N2 is entering and 20 mole percent CO2. This is the feed. And inside this absorber column, there is sodium hydroxide solution, all right, which is completely absorbing the CO2 that is entering. Please note, the CO2 is getting completely absorbed by NOH, and this reaction is happening, all right, inside the column. So, what's the reaction? Let's write the reaction. Reaction is CO2 plus 2NOH gives sodium by sodium carbonate plus water. Here the reaction is happening, and after the reaction, two things are coming out. First, there is a liquid stream and it is coming out at the rate of 1000 grams per hour. So the product is coming out at 1000 grams per hour. Let me write the reaction here. And that is the flow rate, the mass flow rate of the product, and it consists of sodium bicarbonate, sodium hydroxide, and water. So, sodium bicarbonate, sodium hydroxide, and water. Sodium bicarbonate is 26.5 weight percent. Sodium hydroxide is 4 weight percent, whereas water is 69.5. All right. So this is the overall question, and what is coming out? Pure nitrogen is coming out. Okay, This is the top, this is the bottom of the column. Let's do one by one. First, we have to calculate the moles of Na2 formed. A. Moles of Na2CO3, sodium carbonate formed. Moles or mass? Yes, moles. So, this is what we have to find. This is part 1. So, before proceeding, I should first take a basis for this problem. The basis is quite obvious. It will be the product flow rate, 1000 grams per hour product solution. This is the basis. So in the product, mass of sodium carbonate. What is the mass of sodium carbonate? It is 1000 into 0.265. That is 265 grams. That is the mass of sodium bicarbonate in the product stream. So then how many number of moles? You just simply have to divide this mass by molecular weight of
Molecular
sodium
weight.
bicarbonate. Yes, yes, you're correct. So what is molecular weight? It is actually close to 106 gram per mole. Okay, you can calculate later on and check. So if you do this, you will get 2.5 moles or gram mole, right? This is the answer for part 1. Is it clear?
Yeah, it's clear.
Yeah. Now let's go to part 2. What is the mass of NOH input? Means how much of the NOH we have provided in the column for the reaction to happen. So mass of NOH input. Okay. So let's look at the reaction. So in the reaction, what we need 2 moles of NOH to get 1 mole of sodium carbonate, right?
Correct.
So how many moles of NOH is required when we are given 2.5 moles of sodium bicarbonate? So question is how many moles, a number of moles of NOH required for 2.5 moles of sodium carbonate? It will be 2 by 1 into 2.5. So we need 5 moles. So for completing this reaction, we need 5 moles of sodium hydroxide in order for 2.5 moles of sodium carbonate to be formed. Okay. So if we then calculate the mass of NOH required, it will be it will be 5 moles into what is the molecular weight of NOH? It is 40. Okay. So we need for 200 grams of NOH for this reaction. Okay, and in the product stream we see NOH, some NOH is coming out. So mass of NOH in product, it will be 1000 into 4%, that is 0.04, that is 40 grams. So we know input is equals to output, but here reaction is also happening. Then how is this reaction, uh, how is this equation changed? Some of the NOH is consumed, right? So mass of NOH is consumed or reacted mass. This is how the mass balance equation would look like. So input will be equals to, we know, is it clear what I'm trying to do?
Yeah, yes.
Yeah, I'm sorry, wait. Uh, so in the product it is this mass input. So we just have to simply calculate the mass input. This will be uh 200. This is the required amount plus 40. Yes, this is correct. So why I added these two values? Because in the product we know what we are getting, and we know how much of the NOH is required for the reaction. So if we add these two, we will get how much of the NOH we should add in the beginning of the reaction. Okay, I hope I didn't confuse you. If there is any doubt, let me know.
No, okay.
Okay, yeah. Now this is part B done. What is part C? Input of water, mass of water input. This is the question. So if we look at the reaction again, we will see water is produced in the product, and for every 1 mole of sodium carbonate, 1 mole of H2O is required. If you see this in the product, 1 mole of sodium carbonate requires, or along with 1 mole of sodium carbonate, 1 mole of H2O is formed. So they are equivalent, 1:1 ratio is there. So we know that in the product 2.5 moles of sodium carbonate is produced, right? In the product from part A, we know this. So how many moles of water will be there? Did you get the question? So in the product, we saw that 2.5 moles of sodium carbonate is produced. And stoichiometrically, according to the reaction, 1 mole of sodium carbonate gives 1 mole of water. So how many moles of water will be there that we get from the reaction? So moles
2.5.
Sorry, come again. Moles of water produced from reaction. Again, I'm repeating. From this part A, we know that 2.5 moles of the sodium carbonate is produced due to the reaction, right? This has produced due to reaction. And according to this chemical reaction, 1 mole of sodium carbonate requires, or along with 1 mole of sodium carbonate, 1 mole of water is required. So if 2.5 moles of sodium carbonate is produced, then how many moles of water
2.5
will be?
moles.
Yes, yes,
2.5
correct.
moles of
Right. So 2.5 moles of water is produced from the reaction. So what's the mass of this? 2.5 into 18. It will be 45 grams. 18 is the molecular weight of water. Now, apart from the reaction, some water is also coming out, okay, the product stream. So let's calculate the mass of water in product stream or output that is coming out from the bottom. It's 1000 into 0.695 is 695 grams. Sorry. So input, how much will be there? How much will be required? Input water. I'll use the mass balance equation. Output water minus the produced, or this is more clear. Output water will be however water is coming in input plus H2 that is produced. This is a more clearer way to represent the situation. Okay, so we know the output water 695 grams. We don't know the input. So and not product, it is produced. Water that is produced is 45. Input water will be 695 minus 45, 650 grams. Okay, is it clear?
yes.
Um, Part C we are done. A, B, C. Now D. Mass of NOH input solution. We have to calculate. Hello, I'm back. I'm momentarily disconnected from the meeting because of internet issues. So I'm back. Sorry, I was talking about part D, mass of NOH input solution. This we have to calculate in grams per hour, means it will be a mass flow rate, basically grams per hour. So for this, we have to basically consider two things. So this is an input solution, means it is solution form. NOH plus water will be there. Okay. So previously we have already calculated the mass of water input. Did we calculate? Yes. We also calculate the mass of NOH input in part B. This is part C. Mass of NOH input. This is coming from part B. So if we just simply add these two values, 650 plus 240, we'll get 890 grams per hour. Okay, so this is the value for part D. All right. Now part E, mass flow rates of input gaseous streams. Now tell me, in this particular reaction, what are the gases that are coming in? Or in this particular absorbable column, what are the gases that are coming in?
Nitrogen and CO2.
You're correct. CO2 and N2. Okay. So, but we don't know the exact values of number of moles or mass of CO2. So we have to calculate it based on the chemical reaction. So from the reaction, what we know 1 moles of NO2CO3 will be produced when 1 mole of CO2 is supplied. So we know 2.5 moles of NO2CO3 is produced, all right, is produced in the product. So for this, there must be then number of moles of CO2 in input will be 2.5 moles. Okay. So and we also know from our question that all of this CO2 has been completely absorbed. Means all of the CO2 has been reacted. Since CO2 is completely reacted, okay, so this will not go in the output. CO2 will not be present in output. No CO2 in outlet that is coming from the top. Now let's try to get the number of moles of N2 in input. How shall we do that? So we are given that 80 mole percent N2 is there and 20 mole percent CO2 is there. So let's try to think in this way. For 20 mole percent CO2, we require 80 mole percent N2. We have 2.5 mole percent CO2. So N2 will be 80 by 20 into 2.5. So this will be the number of moles. It is coming out to be 10 moles. So 10 moles of N2 is there and 2.5 moles of CO2. Now we just have to calculate the mass of each of them and add it. That will give the mass flow rate of the inlet gas. Okay, so 2.5 into molecular weight of CO2 it is 44 plus 10 into molecular weight of N2 it is 28. So 2.5 into 44 plus 280, 390 grams per hour is the total mass of inlet gas that is going in per hour. Now part E is also done. Any questions?
No.
No. Now part E. So now we have to calculate the mass flow rates for output gaseous streams. F. Mass flow rates of output gas streams. Okay. Now output, what is coming out in the gas form? N2, right? Nothing else. Only N2 is coming out.
Yes.
So yes. So we already saw in part E that 10 moles of input of N2 is there, and since we know N2 is inert, so moles of N2 that is going in, that will be same as moles of N2 that is coming out. All right. So first let me write moles of N2 out is 10 moles. Then mass of N2 out and into 28, sorry, 280. So it will be 280 grams per hour. Okay, so this is the out and this is for in. Now you can check this particular step whether you have done correctly or not by doing a simple LHS is equals to RHS. So here input is equals to output. If you check, this is your LHS, RHS, right? So LHS, that is what is the input that is going in particular in this particular absorber column. NOH is going in CO2, N2, and some water. Okay. So these are the inputs. Mass of CO2, N2, this is the gas, plus we also provided, along with gas, we also provided NOH and water. So if we add the masses, it will be 390 plus what is the inlet mass of water plus NOH, it is 890. Eight ninety plus 390. 1280 grams. What is RHS or output? Output, in output you see sodium carbonate, right? And some water. Oh, we already know the product weight. This total weight is 1000. So this 1000 contains the sodium carbonate, water, and NOH. And another output that is coming out is the pure nitrogen gas, which is 280. We calculated just here, and it is coming out to be 1280. So in this way, you can check yourself whether the values that you obtained so far up to part 5 or 6, whether they are correct or not. In the entire process, whether the input mass is equals to output mass or not. In this way, you can do a simple checking. And any other parts left? Yes, there is one more. Part G. So here you have to calculate the percentage excess NOH. How much excess NOH that we have supplied. Percentage excess NOH, right? So we know from part B that 5 moles of NOH is required for this reaction. Means we need 5 moles of NOH to get 2.5 moles of sodium carbonate. Moles of NOH required in reaction is 5 moles. Okay, so what will be mass then? 5 into 40, 200, sorry, it's 200. Um, okay. Now we have also done one more thing. Yes, we have calculated the total mass input in part B only. Yeah. So we don't need to do this part again when we already have it. Mass of NOH input is 240 grams. That is in part B. And how many number of moles does it correspond to? Moles of NOH in input will be 240 by 40. 40 is the molecular weight of NOH, so 6 moles. And we require in reaction five moles. So percentage excess will be 6 minus 5 by 5, 1 by 5. I always forget to multiply with 100 into 100. So it will be 20%. Okay, is it clear?
Yeah, clear.
Mhm. So we are done with the third question. This is the fourth one. If there Any doubts or something like that, let me know. Okay. So quickly have a read yourself. So in this question, what is mentioned? It is mentioned that we are manufacturing hydrofluoric acid, HF, by treating this ore, fluorspar ore. Okay. And this fluorspar ore is basically CaF2. This ore is treated with excess of sulfuric acid according to this reaction, and that gives the product HF. The ore that we are using, it consists of 78% CaF2 and just 22% is the impurities. The acid solution that we are using in this case contains only 95% of H2SO4. The reaction completes completely, like it goes to completion, and whatever HF and water that is produced, they are basically boiled, that is volatilized and separated as vapor. And what is remaining? Remaining is a residual sulfate cake, right? It is remaining. And this cake contains 16 weight percent of a hydrofluoric acid. So we are given the basis of 1000 grams of fluorspar. Okay. We have to calculate the values of R, S, and V. So R is the residual sulfate cake, S is the acid solution, V is the vapor. All right. So first let me write the reaction. Reaction is CaF2 plus H2SO4 gives CaSO4 plus 2HF. This is the reaction. The basis that is given to us is 1000 grams of ore, fluorspar ore. Now, let's calculate uh, RS, RS and V one by one. Okay. Part A, what is R? That is, what is the mass of the residual sulfate cake? How shall we proceed? First, let me see what is the mass of CF2 in input. All right, because the amount, the residual cake that we have contains what it should contain. It should contain the impurities, right? And it also contains H2SO4. That is the composition of the residual sulfate cake. Whereas CF2, it has been completely utilized for production of CaSO4 and 2HF. So first let me write the composition. of R. R contains ore impurities, then it also contains CF2, H2, and H2SO4. Not H2, H2SO4. This is the composition of R, and H2SO4 is the 16 weight percent. And we we know that 78 weight percent CF2 is there, but some of it has been used for getting HF. So that we have to subtract later on. Okay. So let's consider first part CF2. So mass of CF2 input is 1000 grams is the weight of the ore. In that 1000 grams, there is 78 weight percent CF2, right? That will come out to be 780 grams. So what is the number of moles then? Moles of CF2 input will be weight by molecular weight of CF2. So molecular weight of CF2 is 78 gram per mole. Right? You can calculate it and check yourself as well. So that will give you 10 moles. So 10 moles of CF2 is being given. Then mass of impurities. What is the mass of impurities in the ore? It is 1000 into 22%. All right. Now, this is input. Impurities are inert. It is clearly mentioned. Impurities are inert. So whatever input mass of impurities there, that will be same as the mass of impurities that is coming out. So when I wrote the composition of residual cake, the mass of ore impurities is calculated. It is 220 grams. Right? But we still don't know the mass of exact mass of CF2 that is inside the cake. All right, we only know the total input of CF2. All right, so let's do this. Let's frame an equation to get the value of R. Input, if we check input side, mass of CF2 plus mass of impurities. No, before we do that, I missed one step. We have to first calculate the CF2 that is being utilized in part of the reaction. So for that, we have to see the chemical reaction. From the reaction, we know 1 mole of CF2 is required to get 1 mole of CaSO4. Yes. So CaSO4 is the component that is in the cake because it's the product. CF2 is being utilized. Sorry if I've confused you. And the input that is in the ore is CF2 that is being reacted completely, and what we are getting is CaSO4. That's the sulfate cake. So 1 mole of CF2 produces 1 mole of CaSO4. So moles of CaSO4 in R will be 10 moles. If we cal for calculating the mass of CSO4 in A, R, it will be 10 into the molecular weight. So the molecular weight of CSO4 is 136 gram per mole. Right. So we know this, we know this. H2SO4, we know the percentage, all right? So we have to frame an equation in order to get the value of R. First, let's calculate the sum of CSO4 mass and impurities. 1360 plus 220. It is 1580. All right. And what else? H2SO4 we know it will be 16% of R, right? We know it will be 16% of R. So rest 84% of R is the sulfate and the impurities, calcium sulfate and the impurities, or we can write it as 0.84 R is 1 is equals to 150. So the value of R will be 1580 by 0.84. So if we do this, you'll get 1881 approximately. Is it clear? Is it clear? Hello? Are you there? Hello? Am I audible?
Hello? Yeah. Yeah, you are audible. Yeah.
Yeah.
Yeah, it is.
So
Yeah,
did
it is clear. Yeah.
yeah, yeah. Now for part B, where we have to calculate S. S is the total acid solution that we are given. So for that, first let's calculate the H2SO4 in R. We already know the R, so it will be 0.16 into 181. So it will be 301 grams. This is the H2SO4 that is there in R. Okay. And since S is a total acid solution that is we are providing as an input, so that's why we have to know how much of the acid is coming out in the cake. That is why we calculated the H2SO4 in R. So mass of H2SO4 input will be equal to mass of H2SO4 that we have consumed due to reaction, that is reacted, plus mass of H2SO4 unreacted, that is in cake. This will be the total input. And this is how we will calculate S as well. So in order to get mass of H2SO4 reacted, what we have to do, we have to go back and look at the equation. So we know for 1 mole of for 1 mole of H2SO4, we need 1 mole of CaSO4. All right. We already calculated the moles of CaSO4, that is 10 moles, right? So we would need 10 moles of H2SO4 as well. So 10 into the molecular weight of H2SO4, that is 98. So 980 grams of H2SO4 will be reacted. Mass of H2SO4 unreacted is 301 grams. So input H2SO4 980 plus 301, 1281. Now we know that 95 weight% is there in S of H2SO4. Okay, we know the acid solution S contains 95 weight% of H2SO4. So we did calculate the total, but of this total, only 95 weight% is there. This is the equation that I framed. So 95.95 into S is equal to 1281. That is the input. All right. So then actual value of S will be 1348 grams. Okay, is it clear? Is this part clear?
Yeah.
Now lastly, we are left with the vapor V. All right. The vapor contains all water and HF. All right. The vapor contains the water and HF. So first, we have to get how much HF is produced from the reaction. So moles of HF produced. What is the moles of HF produced? We know from the reaction that 2 moles of the HF will be produced for every 1 mole of CaSO4, right? So we already have the number of moles for CaSO4. So for HF, there will be 20 moles. 20 moles of HF will be produced. Mass, what is the mass of HF now? The 20 into molecular weight. The molecular weight of HF is 20. Okay. So 20 into 20, 400 grams. All right. So 400 grams of HF will be produced as a part of reaction. Then water. Another component in the vapor is water. So water, from where the water will come in this reaction? Can you guess? In this reaction, from where the water will come?
Due to H2O,
Sorry, can you repeat?
due to H2O support.
H2SO4 solution, acid solution. Is it what you're trying to say?
Yeah.
Yeah. So in the acid solution, there is water. You're correct. So 95 weight% was H2SO4. So 5 weight% of S will be water. So mass H2O input will be S into 5 weight%. It is 1348 into 0.05. As we have calculated here. So it will be 67 1348 into 0.05, 67.4 grams of water input is there. Now, since water is not taking part in the reaction, so how much water you are giving, that much water is coming out. So vapor, mass of vapor V will be mass of HF produced plus mass of water output. 400 plus 67.4 will be 467.4 grams. Right? Is it clear?
Yeah.
So we have calculated all the three variables. Now, lastly, we have to calculate the percentage excess of H2SO4. How much excess of H2SO4 is there? So let me quickly check our previous calculations. Okay, so we have calculated in the residual cake that there were 301 grams of H2SO4 that was coming out. Also, we calculated the input H2SO4, how much H2SO4 we are giving. So it was 1281 grams is the input. So let me quickly write it. H2SO4 mass input is 1281 grams. Right. And since for this part we have to convert mass into moles, So moles input of H2SO4 would be 1281 by molecular weight. So molecular weight of H2SO4 is 98 divided by 98. There will be 13.07 moles. Now from the reaction, yes, from the reaction, what we see is you need 1 mole of H2SO4 to get 2 moles of HF and 1 mole of CaSO4. So we already know the moles of CaSO4 that is produced, that is 10 moles. So that means you would need 10 moles of H2SO4 from reaction. Required is 10 moles. So excess, percentage excess of H2SO4 is equals to 13.07 minus 10 divided by 10. So this will be 100. Sorry, I always forget to multiply with 100. 200. This will be 30.7%. Okay, is it clear?
Yeah.
So we have like already completed 2 hours almost. So this is another question, but it will take some time. So I'll keep this question for the next session. Uh, you can take a screenshot now and try it yourself before that, but I'll discuss it in the next session. But if you have any questions regarding the questions that we discussed,
No.
no? All right. So I hope you enjoyed today's session. If it got boring, I'm sorry for that. This topic is like that. Like you have to practice, and
Yeah,
more you
understand.
practice, yeah, the more you practice, you will learn better actually. I can only show you few questions, but it is up to you to practice more. And if you have any queries, let me know in the next session. If you face difficulty in solving any question, I'll try my best to help you out. And yeah, thank you for joining. I hope I'll see you in the next session. Right.
Okay, thank you so much. And
Yeah.
next session also we are giving same problem like that.
Yes, similar. So in the next week, let me. So week 4, if you see, they've started a new topic, all right. But I'll try to do some more material balance questions first, all right, and then I'll continue with the new topic. So there is biochemical reactions, enzyme kinetics have started, cell growth kinetics have started. So these few new topics are there, but don't worry, I'll take up few more material balance problems with chemical reactions so that you get more idea or more practice on what type of questions are there in this particular topic. All right. So
Yeah,
this is
sure.
one
Thank.
question this is one question that is based on the extent of reaction. So that I'll discuss in the next session. Apart from that, also I'll try to come up with few more questions on this topic. And then we'll proceed with the new one. All right.
Okay.
Yeah.
Okay, thank you
Thank you.
so much. Thank you.
Yeah. Yeah.